Welcome to What Matters, Princeton Foundation for Peace and Learning's brand new video series. In this series of interviews and panel discussions, we discuss various social issues and solutions thereof with the global experts in fields of women empowerment, education, healthcare, and world peace. Professor Niraj K. Jha is a distinguished academic in the field of electrical and computer engineering, currently serving as a professor at Princeton University. He earned his B.Tech degree from the Indian Institute of Technology, IIT Kharagpur, in 1981, and his Ph.D. from the University of Illinois at Urbana-Champaign in 1985. Professor Jha's research spans several cutting-edge areas, including smart healthcare, machine learning, cybersecurity, and the Internet of Things, IoT. His contributions to these fields are substantial, with over 480 published papers, 16 award-winning papers, and over 28 US patents to his name. In addition to his research, Professor Jha has also co-authored 5 widely used books in his field. His outstanding contributions have been recognized through various honors, including being named a fellow of both the IEEE and ACM. He has also received the Distinguished Alumnus Award from IIT Kharagpur and the Princeton Graduate Mentoring Award. Beyond academia, Professor Jha is also a co-founder of 2 startups, NeuTigers, which focuses on innovations in smart healthcare, and Illumia AI, which focuses on graph language models, and knowledge graphs. His involvements extend to several influential roles, such as serving as editor-in-chief or associate editor for multiple IEEE transactions. Professor Jha has also served as associate director of Princeton's Andlinger Center for Energy and the Environment. Professor Jha's extensive experience and impact make him a leading figure in his field, with a career dedicated to both pioneering research and mentoring the next generation of engineers and innovators.
I'll talk about the Internet of Things hierarchy, and then talk about the different aspects of smart healthcare, starting with sensor-based disease detection. And to do this disease detection, we need some machine learning tools. So I'll briefly talk about what are the machine learning models that support this activity. In healthcare, interpretability of the predictions of the models is also very important. So we'll talk briefly about that. And then talk about personalized medical decision making, where the decisions, the interventions, the therapies that are recommended can be personalized to each patient. And then we'll conclude. So here is the Internet of Things. There are about 10 billion things, and these things correspond to sensors and actuators and processors that are connected to the internet, as opposed to just 5 billion humans that are connected to the internet. And the goal of IoT is to make everything smart by bringing AI and machine learning into different cyber physical systems like homes and buildings and grids and transportation, medical devices, surveillance, infrastructure, and so on. So generally, this is the hierarchy of IoT. At the bottom, you see the edge nodes. The edge nodes imply that they are smartphones or smartwatches or devices that generally operate on battery. The sensor data are sent to these edge nodes, or they may reside in the edge nodes. And these sensors can communicate with each other. So there's local computing going on, which is edge computing, but that is not going to be very comprehensive because I don't have enough energy for heavy-duty computing on these edge nodes. So I collect the data and transmit it upwards to the cloud. And so this has been the current paradigm of IoT. The problem with this paradigm is that it takes a lot of energy to transmit all the data to the cloud, or at least most of the data to the cloud. And today we collect about 4 zettabytes of data. Zeta is 10 to the power 21. So that's a lot of data that are being transmitted to the cloud. Unfortunately, we are able to make or take advantage of only 2% of that data. 98% of the data are just wasted. So this paradigm is not working, will not work in the future, where by the end of this decade, we'll be collecting about 100 zettabytes of data per year. So in the future, instead of data bubbling up, the sensor data bubbling up to the cloud, we will have intelligence bubbling up, which means the local sensors, the local edge devices, they themselves will be smart. They'll have a lot of machine learning models, AI, embedded in them. So that will lead to enhanced personalization. It will need to enhance privacy and security and less latency and less requirement for network bandwidth. So this new paradigm would be process data where they are collected. So you don't have to spend the time and energy and latency transmitting data. And so this will lead to hierarchical paradigms for where you have some intelligence on the sensor, some of the intelligence is on the smartwatch, some more intelligence is in the cloud. So there will be a collaboration among these different levels of the hierarchy to come up with the correct inference. So what is smart healthcare? It's really another name for AI or machine learning in healthcare. Machine learning is a subset of AI, and that has led to huge growth in the AI industry in the last 10 years or so. Before that, the AI industry had ups and downs, but it's really been on a growth curve for the last 10 years. The goal in smart healthcare is use all these new technologies that are becoming available, sensors that are now in small form factors in your smartwatch and smartphones, different types of medical images, MRI, CT scan, ultrasound, X-ray, to take advantage of these modalities to do disease detection. So distinguish disease from healthy status. The next step is not just distinguishing disease from healthy status, but also doing differential disease diagnosis, which means distinguish COVID-19 from flu. Then the diagnosis has been done, and the physician has to keep the patient well. Maybe the patient has been diagnosed as depressed, but there can be very extreme manifestations of depression. So the psychiatrist would like to make sure that the person is not going into extreme manifestations of that condition. That means the data or the inference on the data should be available to the health server, where the physician can access the result, not the raw data, but the result of the processing of the raw data, and make sure that all the patients that he or she has are doing well on that day. Then I mentioned interpretability is very important in some applications, like in medicine and law and education and business. So can we figure out what therapy works individually for each patient? So let's start with smart healthcare, which is sensor-based. The conventional healthcare in this country is highly centralized. We are spending more than $4 trillion on healthcare per year, and 1/3 of that goes into hospital care. This is very time-consuming. We don't get timely interventions, very inefficient. We spend twice as much per capita on healthcare as compared to other advanced countries. And this is non-pervasive. So not everyone is getting this benefit of all the technologies. So can we go beyond these problems and bring in AI and machine learning so that we can alleviate some of these problems? Now, I mentioned various wearable medical sensors. These are now integrated into our rings and watches and phones. Some of the examples are a heart rate sensor, a pulse oximeter, skin conductance, ECG, skin temperature, and so on. About 8 to 10 sensors in your smartwatch, about 15 to 20 sensors in your smartphone. So now a lot of sensors are on our body. Can we take advantage of that for doing disease detection? So to do that, we can collect the data, these physiological signal data, and then train sophisticated machine learning models on that data. And these models become predictive of the disease or the condition, and they are very energy efficient. So they can be placed in your smartwatch, embedded inside an app, and you can access the neural network, which is the machine learning model, from the app itself very quickly. Within a minute, you can get a decision whether you have that condition or not. So to be able to do that, let's dig a little bit deeper. We have developed a system called Health Decision Support System, HDSS for short, where we have tier 1, where you're outside the clinic, and most of the time we are outside the clinic, but we are wearing our smartwatch or smartphone, and it has all these different types of sensors, and we are able to distinguish healthy from a particular condition. And you could be monitoring many different conditions, many different diseases in parallel, as we'll see later on. So suppose tier 1 has found out that we have an onset of a disease or onset of a condition. Then we are sent across the clinical boundary to tier 2. Tier 2, now you're in the clinic. Clinic has access to your electronic health records. It may have access to some simple measurements, but that may not be enough. So then you're sent to tier 3, where maybe a CT scan is needed, maybe a blood test is needed. And finally, the diagnosis is done. It's time for the treatment suggestion, and as well as prescription suggestion and lifestyle suggestions. Now, each of these tiers for any particular condition will have a machine learning model that will be part of the diagnosis engine. And there are different ways of implementing these models. But the key is that all these tiers, the raw data, because now from tier 1 to tier 2, I have more data, tier 2 to tier 3, I have more data, and tier 4, I have even more data. So at each level, I can have a more sophisticated machine learning model for a given disease. So that's how we build the models for every disease. To give you an example of tier 1, for COVID-19, so here the aim is to distinguish COVID-19 from the healthy status. And you can see the inputs, for example, blood pressure, galvanic skin response, oximeter, that's blood oxygen. These are the inputs, skin temperature, and there are other sensors not shown here. And there's also a questionnaire, yes, no answer, cough, fever, etc. Now, in the medical domain, we are never able to get enough data. So the first part of the pipeline says, let's collect some synthetic data, which has the same probability distribution as the real data. And then after we've collected the real data and the synthetic data, together we train a neural network. And I'll talk about how you train the neural network. And finally, you get a neural network architecture that you embed in your smartwatch or your smartphone, and then you access that through your app. So for the COVID-19 problem, we collected data from 87 individuals in Italy. This was at the peak of COVID, May of 2020. The data collection is about 1 hour of data per patient. So you just place the sensors, the smartwatch on them, and collect the data. And you can see the data that were collected on the right-hand side. There are 11 questions, and these are the sensors at that time that were in the smartwatch. Now, some of these sensors are also embedded in today's technology. For example, Samsung smartwatch. And these are the data collection sources. After we train the neural network, you can see this is called a confusion matrix, where on the diagonal, the numbers represent true positives and true negatives. And if it's off diagonal, then that's an error. So here you can see that most of the error comes from this number 54, where C2 is the cohort 2, which is asymptomatic COVID patients. Some of them are being predicted as healthy patients. So that's where some of the errors are coming from. But overall, the accuracy was more than 98%. The false positive rate was less than 1%, and false negative rate was less than 5%. So this is just one example, but we could do something similar for other diseases as well, as we'll see. So here is a look at how the app looks, where quickly you can answer the questions. In fact, you can answer no very quickly by one tap. And the data collection happens at runtime, at inference time, for about 1 minute. The sensor data are transmitted automatically to the neural network, and neural network takes another 60 milliseconds or so. After that, you get the positive or negative prediction from the neural network. So this is how this works. We had done similar experiments for diabetes. How do you distinguish type 1 diabetes from type 2 diabetes from healthy status? And we had 96% accuracy for that. And we'd also looked at mental health disorders. For example, bipolar disorder, depression, schizophrenia, and there the accuracy was more than 90%. And all these technologies are being commercialized by the startup called NeuTigers. And it's looking at more than these three diseases or conditions. It's looking at many other diseases as well. So let's go on to healthcare applications, where I may want to do medical imaging-based disease detection. There are lab results that will come in from tier 3. The patient himself or herself could be offering new health data. Examination uncovers some more symptoms, and there is inpatient health monitoring at the clinic or the hospital as well. The problem with this is ideally what we want, but the problem with this is that this data is difficult to collect. There are lots of laws, privacy laws. You can't take the data out from a country, or so we have to honor those laws. Hard to gain access to all this data because from clinic 1, if you collect the data, you cannot take it out and combine it with data from clinic 2. Expensive to acquire. And it may be time limited. Maybe for some amount of time you have access to the data if you train the model inside the clinic, but after that you lose access. This way you can build task-specific models for smart healthcare, but only if you can overcome some of these problems. So can you fine-tune an architecture to mitigate some of these problems? So let's look at a concept called catastrophic forgetting in machine learning models. And this refers to the fact that in a neural network, which is patterned after the human brain, so each of these circles is a neuron, and layers of neurons are connected with each other. So let's suppose we train this artificial neural network with disease 1, for example, COVID-19. Then when we get new data for diabetes and we retrain it, it forgets about how to diagnose COVID-19 or how to detect COVID-19. So that is called catastrophic forgetting. So then it becomes difficult to train on newer data sets if the model keeps forgetting about the old data sets. So in addition, the probability distribution of the data that you trained on may not be the same as the probability distribution of the data you see in the field. So that reduces accuracy. Maybe you've added new classification classes. For example, maybe the original data was on symptomatic COVID and healthy, and now you've collected data on asymptomatic patients, so you've added a new classification class. We don't want to train from scratch, so can we do this incrementally? There may be a stream of distinct tasks. So I have one disease, and the next disease, and the next disease. So traditionally what I would do is, for each disease, I would have a separate model trained. So if I have 10 diseases that I want to track, and I can have a library of these modules that I can download depending on what diseases I want to track on my smartwatch. So the problem with this approach is that the memory storage goes up, then the energy consumption goes up, and the detection process itself becomes more complicated because now I have so many models in my edge device. So what we want, and this we call it a doctor framework, is an ability to continually train a model incrementally while avoiding the idea of catastrophic forgetting, So that's our doctor framework. You can use this pervasively. It's timely, early detection of the different onsets of different diseases. It's very energy efficient. It will have one body and multiple heads. So you can see this is the body of the neural network, and this may correspond to one disease, this one may correspond to another disease, this one corresponds to the nth disease, and so on. But it's a very small form factor. Adding an extra head only accounts for maybe 2-3 kilobytes of extra data, so the memory consumption does not go up much. So now this becomes very energy efficient, and it can be continually trained. It doesn't forget about the previous diseases. As an example, we have implemented this doctor framework where simultaneously it can tell you, are you asymptomatic or symptomatic for COVID-19? Are you type 1 or type 2 diabetic? Or do you have depression or schizophrenia or bipolar disorder? You can keep adding more and more heads as you collect more and more data. Now, let's look at machine learning tools that undergird these different frameworks, COVID-deep, dive-deep that I talked about. So the basic idea is how you come up with or how you synthesize these neural networks is that you have a seed architecture, a seed neural network, and you add some neurons and connections to increase the accuracy, and then you prune away some of the neurons and connections that are not necessary for high accuracy, and then you end up with a final architecture. Of course, this is a very simplification of the actual procedure. The actual neural networks may be much larger, but this is the essential idea. And the inspiration actually comes from the human brain. So if I had asked you if you could guess at what age you were the smartest, I'm not sure many of you would guess at age 2. When you were a toddler, you had the most connections and most neurons in your brain. So we take inspiration from that. We start from a baby neural network. We grow it to a toddler neural network, which becomes very accurate, but it has too many neurons and connections. And then we aggressively prune it by about 2 orders of magnitude into an adult neural network, which is good for that particular application, but it's not good for other applications. So that's the idea of how to synthesize these neural networks. And that framework is called SCAN, where it has these different steps. How do you grow the connections among neurons? How do you add neurons? How do you prune the connections? And there are different schemes that allow you to do that. And this results in about 100 times smaller neural network than the traditional neural networks, where you have layers of neurons connected to each other fully. Now let's go on to interpretable machine learning predictions, because if I go to a physician and I say, well, my neural network is 95% accurate, they are still concerned what happens in the other 5% of the cases. I don't want that other 5% when the neural network is making an error to negatively impact my patient. So I should be able to not just give the prediction, but also explain how I got that prediction. So this is something that we've recently done. We call it the differentiable logic networks. It's a big departure from traditional neural networks. And here in traditional neural networks, you basically look at the weights on these edges. Here there are no weights on these edges. You have some input neurons that convert the continuous and categorical features into binary features. Then you have some logic gates inside, the logic neurons inside, where you only take advantage of logic that has and or not. Very easy to explain when A and B is true and C is not true, then the output is true. So it's very easy to explain that. And in the output layer, you have a sum of arithmetic sum of whatever the inputs are. This gives us a network which is 1,000 times smaller than the traditional, even optimized deep neural networks. Now, to explain how this makes things explainable, this is the network that this method generated. There was a data set on diabetes that had 14 inputs. This methodology said, well, out of the 14, only 5 are important. It threw away the other 9. So it looks at inputs like cholesterol to HDL ratio, waist size, glucose level, age, and so on. And these are connected with each other using NOT and OR neurons. Very easy to explain. Class 0 is no diabetes and class 1 is a diabetes prediction. And here is the formula. The diabetes prediction is the ratio cholesterol to HDL is greater than or equal to some number, or glucose is greater than or equal to some number, or age is greater than or equal to some number of years, and waist size is greater than or equal to some number of inches. And they have some weights associated with them, and whichever one gets a higher score, that is a prediction. So this is very easy to explain to a physician in terms of these features, that this is the reason we are predicting that this patient has diabetes. And the accuracy of this is even higher than deep neural networks. So there is no trade-off. You're getting a much smaller network, much more energy and latency and memory efficient, and you're not paying a price in terms of the accuracy. Now let's go on to personalized medical decision making. So there's a famous person, Julia Pearl at UCLA. He's a Turing Award winner. Turing Award is the Nobel Prize of Computer Science. And this is from his best-selling book. And he has this ladder of learning, where at the lowest level is association or correlations. Most of the neural networks, most of the machine learning models, large language models, they're based on correlation. So Julia puts that at the lowest rung of the ladder of learning. Next level up is doing interventions. For example, if you're a pharma company, you do randomized control trials to show the efficacy of a drug, where you have to intervene, do something, place someone in the placebo group, place someone in the treatment group, and make sure that you show the efficacy by taking the difference of the averages in those two groups. At the highest level, he puts counterfactuals, where you ask what-if questions. Some intervention has happened. What if it had not happened? What would have happened to the trajectory of the patient? He places this at the highest level, so this is the most accurate in his view. So we will look at counterfactual-based decision. The applications are very wide: treatment planning, drug testing, what feature should go into software, which bill should you pass. There may be many policy decisions that you can make, which one is optimal. So you can think of this very broadly. It can be applied to sociology, politics, policy, medicine, law, and so on, wherever you have decision making like this to be made. So to give you a brief background from a high level, let's look at a Nobel Prize that was given in 2021 to David Card. He was one of the winners that year in economics. This was for a Card-Kruger paper that was written at Princeton in 1994. David Card is now at UC Berkeley, but he was at Princeton at that time. And the experiment was something very simple. New Jersey increased the minimum wage, and next door, Eastern Pennsylvania did not. And the conventional wisdom was that if you increase the minimum wage, then your employment suffers. And they found that the impact was minimal. Hence a Nobel Prize later on, because this was unexpected. Okay? So this was basically a what-if question, a counterfactual question. What would have happened to New Jersey had it not increased the minimum wage? And we were getting a digital twin for New Jersey with Eastern Pennsylvania to be able to answer that what-if question. So 10 years later, someone called Avadi and his group presented this with a sound mathematical foundation, where I have n donor units who got the placebo. This is the treatment unit, and maybe the intervention happened here, the vaccine was given here, for example, and the question is, so I have the actual values after the vaccine was taken, but I want to predict the counterfactual values. What would have happened if the vaccine had not been taken, if the intervention had not happened? So this idea is based on linear regression. You take these inputs, predict this, take these inputs, predict this, there'll be an error, you sum up the errors, you minimize the error to figure out what are the coefficients I should use for each of these n inputs. So basically you're getting a spatial digital twin of the treatment unit, and you're predicting the what if question, answering the what if question for that unit. The dual of this is synthetic intervention. This was presented in 2021, where let's say if someone is depressed, there may be a couple of interventions possible. One could be cognitive behavioral therapy, another one could be drug 1, another one could be drug 2. So it takes a lot of trial and error for the psychiatrist to find out which one for a depressed patient is the optimal therapy. They tried one thing, doesn't work, try the next thing, and so on. Instead, what we could do is we could collect data. Let's say we've collected 1 hour of smartwatch data from each person who had a particular intervention. For example, 30 people who got CBT, 30 people who got drug 1, 30 people who got drug 2. And now a new patient has come along. They've been diagnosed with depression, and the question is which intervention is optimal for them. And now we can get a digital twin again with respect to each of the 3 cohorts, and whichever trajectory looks the best for that patient, that is the intervention we would recommend. So the problem is not just spatial, but it's spatial temporal. For example, my ECG data from a month ago would be correlated with my ECG data today. So there is a temporal correlation within a unit, and then there is spatial correlation from other people in the cohort who had a particular intervention to the patient in question. So it's a spatial temporal problem. And you can take these matrices, it's actually 3D, it's called a tensor, where there may be many variables that you're monitoring. And from that 3D data set, can you train something? And we train a transformer. Transformer is an invention from 2017. Transformers are used as the foundation for all the language models like ChatGPT and others. But we use transformer in a very different context, which is to make good decisions. So to give you an example, let's take Friedreich's ataxia. It's a degenerative nervous system disorder, debilitating, fatal, no cure yet. There is a data set available. We know that this is caused by deficiency of frataxin, but there is a recent study that says that calcitriol, which is an active form of vitamin D, can increase frataxin levels and help in this particular disease. Now, there's actually a randomized controlled trial going on in Spain to see if calcitriol would be helpful for this disease. But instead of going towards RCT, what we did was we looked at data from 21 donor units. These are the people who had taken calcitriol, and now we had a new patient, patient 219, and the question was, will calcitriol help this patient 219 or not? So it's a personalized medical decision. There are different metrics to figure out whether the drug is helping or not. For example, I show 4 metrics here, but there are many more, and on all of them, we'll see that for this patient, calcitriol would have been helpful. So for A, B, and C, lower is better. The orange line is the counterfactual prediction, and the green line is the actual prediction. And this vertical black line is where the intervention happened. So in general, you can see the orange line is lower than the green line here. And here, higher is better. So here, the orange line is above the green line. So these metrics are implying that for this patient, taking calcitriol would help with their ataxia. So this is what we call a personalized medical decision making. And you can apply this kind of a technique to other domains as well. It doesn't have to be limited to medicine. So to conclude, smart healthcare or AI in healthcare is still in its infancy. The traditional machine learning models require large data sets for training, and often we don't have large data sets. So there's need for synthetic data and basically generate very highly accurate neural networks even in low data regimes. And there is need for prospective learning in healthcare. Prospective learning has these different pillars. So we want continual learning when we come across new diseases, new classes, new probability distributions. Then we humans have very strong cognitive priors, which means genetically we are endowed with some abilities and also from experience from our childhood. The machine learning models would help, could be helped with medical priors that currently is not very actively used. We humans are very curious. If something out of the ordinary happens, we set it aside and we want to investigate further. Lots of big advancements in science are made because of that curiosity. That also fuels our creativity. But machine learning models typically rely on the average case. They want to excel on the average case, and they try to not worry too much about the 3 sigma or the out of the ordinary cases. And causal inference becomes very important because correlations can only take you so far. We also want to know what caused what, not just what is correlated with what, to make much more accurate predictions. So these elements are also being worked on by many groups, including mine, and definitely smart healthcare can benefit a lot if prospective learning becomes a reality. So thank you for your interest.